Welcome to today's webinar, Designing the Next Generation of Gas Turbine Engines with Converge, brought to you by Convergent Science and our partner at Argonne National Laboratory. Thank you for joining us today for the fourth event of the 2025 Converge webinar series. My name is Matthias Sulis and I am part of the business development team at Convergent Science. I will be your host for today's event. I'm glad I can be here with you today and hear from our speakers and partner at Argonne National Laboratory about gas turbine CFD modeling with Converge. Convergent Science is a rapidly growing computational fluid dynamics software company. Our flagship product, Converge, is an industry-leading CFD solver used around the globe to simulate fluid flows in complex systems. Converge features truly autonomous meshing, which eliminates all user meshing time and helps provide fast, accurate results for our client. Argonne National Laboratory seeks solutions to pressing national problems in science and technology by conducting leading-edge, basic and applied research in virtually every scientific discipline. Through collaboration here and around the world, Argonne strives to discover new ways to develop energy innovation through science, create novel materials molecule by molecule, and gain a deeper understanding of our planet, our climate, and the cosmos. Now it is time to introduce our speakers for today's event, Dr. Debolina Dasgupta and Mingyi Liang. Dr. Debolina Dasgupta is a senior research scientist in the Advanced Propulsion and Power Department within Argonne's Transportation and Power System Division. Her research interest lies in the areas of computational fluid dynamics, multi-phase reacting flow modeling, multi-fidelity machine learning, and high-performance computing for a wide range of applications such as propulsion, power generation, and manufacturing. Mingyi Liang is a senior research engineer in the support department at Convergent Science. He holds a degree from the Colorado School of Mines, where he specialized in computational fluid dynamics, multi-phase flow, combustion, and steelmaking. For the past 2.5 years, Mingyi has been working at Converge, focusing on simulation of internal combustion engines, burner, and gas turbines. During today's webinar, if you have questions for the speaker or the rest of the team at Convergent Science, please use the question box on the GoToWebinar toolbox. Questions submitted during the webinar will be answered at the end. Without any further delay, I will now pass the ball to Dr. Dasgupta and my colleague Mingyi. Thank you all.
Hi, everybody. Thanks for attending this webinar. My name is Mingyi Liang. As Mattia introduced, I am a senior research engineer at the application team of Convergent Science. Today, I am mainly going to talk about two parts. First of all, the advantages of Converge for gas turbine modeling, and second of all, the gas turbine application spotlights. In this part, I will show you some research results from published research papers using Converge software to simulate gas turbine. Then Debolina will talk about her research in Argonne National Lab related to gas turbines. The video on the right is an example of gas turbine application using Converge software. The results is published in this paper from Journal of the Energy Institute. In this research, the author investigated the Liang blowout using two different fuels, the conventional A2 fuel and the alternative C1 fuel. The simulation starts with a high equivalence ratio at around 0.096. And then the equivalence ratio is gradually reduced to see when Liang blowout will happen using these two different fuels. And as you can see here, the Liang blowout happens at an equivalence value of 0.082 for the alternative C1 fuel. However, for the conventional A2 fuel, it happens much later and an equivalence ratio value of 0.074. This research showcases the capability of Converge to accurately predict the Liang blowout and different equivalence ratio values for different fuels. The result is validated with experimental data, and we see a pretty good match. One advantage of using Converge is its autonomous mission capability. For instance, in this video you see on the right, the fuel is injected as Lagrangian particles. It evaporates, mixes with air, and combustion happens. The geometry of gas turbine is usually complicated with very small effusion cooling holes, large combustion chambers, which makes it challenging to manually make the mesh. Converge has the capability to automatically generate orthogonal cells, as you can see here in the center region of the combustion chamber. The mesh is automatically generated, which spares the user time to manually generate it. On top of that, Converge can automatically detect the regions where the change of temperature or velocity gradient is high, and the mesh in those regions will be automatically refined. As you can see here in the close-up view, in the regions where the temperature gradient is high, Converge automatically refine the meshes there. This feature is called adaptive mesh refinement. And it can automatically resolve combustor flow and propagating flames at low computational expense. Converge has models available to account for species-based critical conditions, which is important when your operating condition is close to critical conditions where the ideal gas law does not hold true anymore. Instead of using ideal gas law, the real gas equation of state needs to be used to calculate the gas density accurately. And we need species-based critical conditions as an input for that. Converge also can account for mixture average diffusion, which is important for fuels like hydrogen due to its high diffusion. Converge has transient and steady-state solvers. We have multi-phase models, such as Lagrangian discrete models. As you can see in this video, the fuel is injected as Lagrangian particles. You can also treat this as Eulerian phase using the VOF model. We have advanced turbulence models such as large eddy simulation, LES model, RAS model, and a hybrid of LES and RAS model. Another advantage of using Converge is our detailed chemistry solver, which is efficient even with large mechanisms. It can accurately simulate ignition, premixed flame propagation, Liang blowout, and emissions of NOx, CO, soot, and unburned hydrocarbons in gas turbines. For instance, in this video, you can see that the fuel and air mixture is ignited at the center of one of the burner, and then the flame propagation is successfully predicted by the detailed chemistry. And at the end of the simulation, the flame propagates to relight all the other burners. One problem with using SAGE is that when you have a large mechanism, it's very time consuming. So there are some other simplified combustion models that you can use in Converge, such as FGM model that can be used to simulate gas turbine combustion at a much lower computational cost. However, if your mechanism is small, then there's very little difference between using SAGE and FGM model, and SAGE is always recommended. We have chemistry tools to generate and tabulate ignition delay and laminar flame speed, calculate extinction limits, and generate chemical kinetics mechanisms, which I will talk about it more later. Converge has the capability to do conjugate heat transfer, also known as CHT modeling, which is important to predict hotspots and aid in metal thermal analysis. We also have radiation models, which is an important effect in combustion, in gas turbine combustion, Without it, the temperature tends to be over-predicted because we didn't consider the heat loss due to radiation. Converge has superior scalability, as you can see in this figure, with more number of cores, with our high performance computing capabilities. Converge simulation can speed up linearly. We also have easy CAD cleanup. Our users can generate their surface geometry in the third-party CAD software, such as SolidWorks, and then the surface geometry can be easily imported into our software. And if there's any surface defects, Converge can help you fix those defects by using the proper tool. Converge has multi-fuel chemistry, which is a combination of research results from a few research institutions across the globe. The integrated mechanism is called C3MEC version 3.5, which has 3,700 species and 16,000 reactions. With this is a very comprehensive mechanism, and the user can extract part of this mechanism for a specific fuel, such as you can extract the mechanism for hydrogen, which only has 12 species and much fewer reactions. You can extract the mechanism for ammonia, natural gas, or a combination of multiple fuels. The flame speeds and ignition delays under different operating conditions is validated with experimental results. And the C3 mechanism has polycyclic aromatic hydrocarbon chemistry, which is an important precursor for soot prediction. C3 also has NOx chemistry, which is useful in predicting NOx emission at the outlet of a gas turbine. This video shows how the conjugate heat transfer simulation looks like using Converge. And as you can see here, the fuel is injected as Lagrangian particles. It evaporates into Eulerian gas mixed with air, and combustion happens, which has some high temperature region. This high temperature flame will in contact with the wall and heat that up. The wall has a thickness. The combustor wall has the thickness, and we can see here the temperature of the wall is predicted throughout the thickness using Converge. During this process, we used a feature in Converge called supercycling, which can predict the steady state solid temperature much faster than using a fully transient solver. In the temperature contour on the right-hand side, this showcases a simulation only for the effusion hole. And below this effusion wall is a cold flow, and on top of it is the hot gas flow from combustion. There are some small effusion holes connecting these two regions, and the cold air will flow through these tubes, comes into the hot flow region, forming a thin layer of cold temperature air on top of the effusion hole to prevent it from being overheated and from being melted. This figure shows the temperature on the effusion wall, and we extracted the maximum temperature along the vertical line, along each vertical line, along the streamwise distance from left to right. And we compared the temperature with the experimental data. And you can see a pretty good match here between Converge simulation and experiments. Ignition modeling is important, especially for relight under high altitude conditions. This video shows a simulation where we relight one of the burner and in the center, and the flame propagates from the center burner to all the other four burners. The time used to ignite burner 1, 2, 3, 4, 5 is compared with experimental data. The left bar is the simulation results from Converge. The right bar is the simulation results from Converge. The left bar is experimental data. And we can see that for each burner, the time used to relight them is very close. Another important phenomenon in gas turbine simulation that we need to simulate or study is called flame flashback, especially when we have hydrogen added as the fuel. Because of its high diffusion, and flame flashback is easier to happen. It is critical to predict fuel and flow conditions marking the onset of flashback. The numerical prediction of flame flashback is challenging due to complex interplay between unsteady fluid dynamics and chemistry. So it is important to use both the LAS model and the detailed chemistry models to capture the flashback. The video here shows a simulation where methane, hydrogen, and air mixture comes into the domain from the inlet and the bottom. They go through the swirler, forming a swirling motion, and combustion happens in the combustion chamber. And we can see that flashback happens with the flame crawls into the mixing tube along the center shaft all the way to the swirler blades. This shows a temperature contour of the center cockplane of the simulation. It is clearer than how the flame propagates into the mixing tube. The simulation results match well with the experimental data. These two videos show how the flame shape changes when we change the fuel from methane to hydrogen. So at the beginning, the fuel is 100% methane, and we can see the flame is larger and rounder. And when we gradually change the fuel to 100% hydrogen, we can see the flame becomes thinner due to the high diffusion of hydrogen, which makes the mixing between hydrogen and air earlier. So we have a smaller region of flame front. And also the flame speed of hydrogen is much faster, which tends to stretch the flame, make it look sharper. This video shows a simulation of film cooling. The upper simulation has a higher velocity. So again, below this plate is cold airflow, and on top of it is the hot gas flow from combustion. And we did two simulations with lower velocity for cold airflow coming into the hot gas region. This is a higher velocity, and with lower velocity of cold airflow coming into the hot gas region. And as we can see here, the plate and the center plane, the vertical center plane, is colored only if the temperature is lower than the free stream temperature, meaning that the plate is cooled down. And we can see more region is colored with the lower momentum case. That is because then the cold air coming into the top region with lower velocity tends to stay low and stay closer to the plate, which makes it easier to form a thin low temperature layer on top of it, thus cooling the plate down. Whereas in the high momentum case, we didn't see as much area is cooled down on the plate. The isosurface is a Q-tearing isosurface and is colored by span-wise verticity. We can see more verticity in the high momentum case due to higher velocity and turbulence. Again, the maximum temperature along the streamwise direction is extracted and compared with experimental data. We can see a pretty good match here, especially with K omega SST model, which can predict the near wall flow more accurately than RNG K epsilon model. This video shows the study of Liang blowout for methane and hydrogen at different adiabatic flame temperature. With methane, you can see the Liang blowout happens earlier at 1450 Kelvin adiabatic flame temperature, and with hydrogen, it happens later at 1305 Kelvin. The results match the experimental data as well and is published in this paper. Hydrogen gas turbine is of interest as a new application. This is a report from Doosan and Southwest Research Institute, and they use the FGM SAGE 3-point PDF SAGE model to simulate the hydrogen and air combustion in the gas turbine. So the air is injected through these air tubes, and hydrogen is injected into these tubes through some smaller tubes on the side of these air tubes. They mix with each other, and the combustion happens in the center combustion chamber. We compared the NOx emission under different equivalence ratio. The triangle is the results from SAGE simulation, and the blue dots are experimental data. And we can see a pretty good match from Converge compared with the experimental data. This slide shows a power generation turbine. This is a scaled down practical power combustor. We have two locations where fuel is injected. They are pilot, which is located at the center of the gas turbine, and another main inlet. The pilot ratio is the ratio of the mass flow rate of fuel of a case to that of the baseline case. For the baseline case, the pilot ratio is 1. So when the pilot ratio is high, that means we have more fuel coming from the pilot into the combustion chamber, and that has higher CO because it is closer to equilibrium state. When we have a lower pilot ratio, the CO will also be higher because combustion is less complete. And this is called CO knee, the drastic increase of CO. And Converge can capture this phenomenon successfully. Usually we don't want the CO to exceed 10 ppm when we reduce the pilot ratio because it usually means Liang blowout or mechanic failure. And Converge can be a useful tool to predict that. For NOx, it is obvious that when we have more fuel coming in from the pilot, the flame is more stable, the temperature in the combustion chamber is higher. NOx is usually generated in high temperature regions. So with higher pilot ratio, we have higher NOx. This is the last example I want to show you, which is noise and combustion instability study using Converge for a gas turbine. So this is a geometry of the simulation. We can see methane is injected through the annulus outer inlet. The mixture of oxygen and water is injected at the center. They mix for a very short distance, and the combustion happens in the combustion chamber. This figure shows that we have enough cells across the heat release region. And when we plot the kinetic energy spectrum versus frequency, we can see most of the energy is in the large eddies. And for small eddies, we have the -5/3 slope shown on this figure, which means we resolved the inertial subrange, and the mesh size is fine enough. In this figure, it shows the pressure fluctuation, which is defined as the difference between the time averaged pressure and the instantaneous pressure. We plot the pressure fluctuation for 9 cycles, which is the blue line. It matches the experimental data very well, which are the black dots. The periods matches each other, but the prediction has slightly lower magnitude. With this figure, we can do a fast Fourier transformation to know the noise frequency and amplitude, which is already available tool in Converge Studio. So that concludes my presentation. I'll give it back to Mattia.
Yeah. Hi, Mingyi. So we will now pass the ball to Debolina so she can go through her presentation. All right.
Okay. Yeah, so thank you again for the opportunity to present. As introduced, I'm Debolina Dasgupta. I'm a senior research scientist at Argonne National Lab, and today I'll be talking about some of the applications in the gas turbine space for which we've used Converge. Before I begin, I would like to acknowledge the funding for the aviation part of the work that I'm going to present coming from Department of Energy's Vehicle Technology Office. I'm also going to be talking about some of hydrogen microturbine simulations that we've done funded by Argonne's Laboratory Directed Research and Development Program. I'd like to thank Convergent Science for the licenses. A lot of the microturbine simulation work that I will talk about today was done by my postdoc, Dr. Joshua Christopher, who's currently at NASA Glenn, and the simulations were performed using computing resources here at Argonne on our Laboratory Computing Resource Center. So I'll first begin on the aviation gas turbines side, specifically focusing on the multi-phase reacting flow side of things. So as has already been introduced in the first half, gas turbines have a slew of complex flow fields that are going on inside within these combustors. You have the spray, you have a complex flow field, then there's subsequently a flame, and all of these are interacting with one another in a very dynamic manner. And CFD can really help understand a lot of these interactions and the governing processes, and then help us further understand, either as we are looking at different fuels, what different fuel behaviors are there, or what design changes might be required. So you can really understand the dynamics at stable behavior and for rare events, which are really sometimes how fuels are assessed in terms of lean blowout, high altitude relight, and cold start ignition, all of which were discussed briefly previously. So the configuration that we are focusing on the aviation side is the AFRL referee rig combustor. So this is a single cup realistic gas turbine combustor with all the different complex flow paths. And again, Mingyi already talked about some of these things. So you have the inflow that's coming in that's split into multiple different air paths, one going as the swirling through the swirler as the swirling air. Then you have the flow that's coming in through the dilution pipes and the effusion air holes. And then there's a fuel injection that's happening in the center. So all of this is leading to this rich burn, quick mixing, and then a lean burn combustor. So this is an RQL type of a configuration, and was developed with inputs from industry partners. It works as a very good relevant reference gas turbine combustor for aviation applications. So a lot of the work that has been done on this in the past has obviously initially looked at some of the validation part of it. So this here summarizes the model's setup details and some of the mesh information, and I'll touch upon the mesh information a little bit again in the subsequent slides. But there's a base grid that we use of 3 millimeters with minimum grid sizes in the primary zone and from the effusion holes, which sits at about 187.5 microns, leading to a cell count of an average cell count of about 21 million cells. So this is using large eddy simulation. So this is not a very coarse LES, but this is also not a very refined LES. So it somewhere sits in that happy middle of really being an engineering LES, which still lets us understand a lot of what's going on in the dynamics of these behaviors. The combustion model we've used here is SAGE with the fuel, which is A2, which is typically a nominal jet fuel. So it has very average or nominal properties of what is typically available as jet fuel. And we've used a mechanism which involves multiple species and multiple reactions. A critical part of doing these gas turbine simulations and getting closer and closer towards predictive side of things is looking at different initializations. So obviously we had the boundary conditions that were very well characterized for the flow that came from the experiments, but we also had information on the spray initialization, which came from PDPA measurements or phase Doppler particle analyzer PDPA measurements done downstream with a way that came from the experimental team itself of extrapolating that information close to the nozzle exit, and that was then done as a series of 6 rings, as you can see in the figure on the left hand side, with the droplet diameter distributions prescribed for each of these 6 rings or 6 injectors, so as to say very close to the nozzle exit. The other information in terms of the spray angle, a hollow cone, and the definitions of the hollow cone, all of that also came from the experimental counterpart. The table summarizes the boundary conditions. As I said, they're very well characterized boundary conditions. And we also had a lot of information of how the airflow was splitting into different sections as well, which I'll cover in the next couple of slides. So first, looking at grid sensitivity, as I said, we started with a mesh with a base grid size of 3 millimeters, and we changed the minimum grid sizes to different levels. And on the right-hand side, you can see the flow split going through the swirler, the dilution holes, and the effusion holes, and how they changed as we were looking at changes in the minimum grid sizes. So you can see when it comes to the swirler, for example, by the time we were at a level 3, which was the 0.375 or 375 microns, we had reached a good convergence for the non-reacting flow. For the dilution holes and for the effusion holes, you can see that that convergence happened somewhere at level 4, which is the 187.5 microns. So based on all of this information, these were the grid sizes that we used with embeddings for these specific regions. In addition to that, we also used adaptive mesh refinement, and the decision for picking what size of level refinement that we would require was determined again by the flame thicknesses and then the swirling flow and the dilution air jets and the interactions that were happening. But overall, even for that one with AMR, we went with the 187.5, which was the level 4 grid refinement. So with all of that grid refinement considerations that I just presented, we looked at the flow split through the different air paths on the left-hand side. These are just the different flows paths through the swirler. So you have the inner axial, the outer axial, radial, and cooling. And we had this information coming in from the experiments. And from the simulation standpoint, we had just divided each of these into separate regions. So we were able to monitor the flow that was going through these different regions. The experiments are presented in blue and the simulations in orange, and the table on the right-hand side summarizes the values. As you can see with the information for the grid that I presented in the previous slide, we see pretty good agreement between the experiments and the simulation. Probably the maximum difference that we see is with the cooling on the cooling flow path, which was a 23% difference. But you do notice that if you look at the numbers are very close to each other between 2.89 and 2.22. We also did this for the bigger flow paths, which was the entirety of the flow going through the swirler, then the dilution air, and then the effusion air as well, with similar the blue with the experiments and the orange with the simulations. And again, we see pretty good agreement between the experiments and the simulations, which gave us confidence in the grid sensitivity and the mesh resolution that we picked. The next that we looked at was looking at the non-reacting spray validations. On the right-hand side, what you see is at different axial location, which are marked by the X, the Sawyer mean diameter or the SMD distributions with the experiments in black dots and the simulations in the red dots. As expected, we do see the anticipated hollow cone characteristics. You can see that there are more deviations closer to the nozzle exit, and as you go further downstream, the experiments and the simulation match better. Part of that is attributed to some of that extrapolation that was done by the experimentalists in order to get us appropriate boundary conditions. So there's still some amount of residual changes that might be happening that need to take over as the flow and the spray were interacting with one another. But overall, at all axial locations, we do see that within the ballpark of what the experiments predict, we do see pretty good trends in the radial distance at these different axial locations. We also looked at the axial velocity, and again at the same different locations. So that's marked by the X. And again, we see pretty good agreement between the simulations and the experiments, particularly close to the nozzle. Further downstream, some differences are noted, but I'll still note that the peak values are captured pretty well. And overall, the trend wherein the peaks are shifting radially outward, that also stays consistent. And then finally, we looked at the radial velocity distribution. And again, close to the nozzle exit with the velocity, we can see very good overlap. And as we move further downstream, again, similar to what was noted for the axial velocity, the trend of shifting peak values radially outward, we still see that between the experiments and the simulations pretty well. And also suggesting that the spray cone angle is modeled well. So overall, the Lagrangian model that we're using tied with the evaporation models in the LES do predict the spray behavior in the near nozzle region reasonably well, which then gives us the confidence to move to the next step, which was the reacting spray flame validation. So here you see the comparison between the flame shape. So on the left hand side is the experimental image, and on the right hand side is the one from the simulations. What you see here is OH star chemiluminescence from the experiments, and in the case of simulations, we compared it with the line of sight integrated OH mass fraction. So this is basically in the Cartesian coordinate systems, basically spatially averaging in the z direction from the simulation standpoint. We overall see that the asymmetry that we see in the flame shape in the experiment is also replicated in the simulations. Obviously, the experimental one shows a lot more of asymmetry compared to the simulation one, but the fact that we are using the entirety of the geometry without any simplifications does mean and does show that we can actually see some of those geometry induced behavioral changes that we would expect in flames can be seen from the simulations. The peak locations where they're occurring, it occurs within the shear layers in both the cases, and the flame anchoring location and spread are also captured pretty well by the simulations when we compare them to the experiments. The next thing that we did was looking at the lean blowout for this fuel, which is A2. So the fuel ramp down procedure is followed very similar to what's done in the experiments. So they typically ramp down the fuel flow rate, and the way we ramped down in the simulations was just using the spray initialization and the mass flow rate control for the spray initialization, and we were stepping that down for different global equivalence ratios. So we went from 0.096, that's where we started, went to 0.09, and then stepped down further, as you can see in the plot on the left hand side. We then replicated the step down process as well once we got to a specific number with a different step size as well, just to ensure that there was not an influence of the step down process on what was being predicted as the lean blowout global equivalence ratio. And an example of that is shown here for the baseline A2, wherein we did the heat release rate is monitored in order to give us what this LBO global equivalence ratio is. And you can see that beyond a certain equivalence ratio, the heat release rate starts dropping significantly. And that was tagged as the global equivalence ratio of lean blowout for this baseline A2. So now that we had a very well validated model starting from the non-reacting spray, reacting, and lean blowout, we then wanted to use this model to understand the influence of synthetic aviation turbine fuels. So as we can understand, like all these fuels have a lot of complex physical properties and chemical properties that influence a lot of the different physics that happens within these systems, starting from the internal flows of the atomization, the vaporization, the combustion, and subsequently having impacts on emissions and contrails. So what we wanted to understand was what was the impact of atomization on the subsequent combustion behavior, because we know that changes in physical properties do impact atomization. So really, this is the question that we wanted to target and understand really. So what we did was we had the baseline spray droplet initialization, and we changed the mean of the droplet diameter by plus minus 5% and then plus minus 10%, retaining the same distribution. We did not do any changes to the fuel physical properties, the spray velocity initialization, the chemistry part of it, or the fuel mass flow rate. So the only thing that we changed was just the droplet sizes and their distribution to understand this impact. So we first looked at global characteristics. The global characteristics here first shows the heat release rate for just the baseline case, which is the baseline A2. Then we overlaid with the minus 5%, the plus 5%, the minus 10%, and then the plus 10%. Overall, you can see that there's not a significant difference that we see in the global characteristics in this case. One of the reasoning for the not a significant change in the global characteristics is tentatively because the operating condition that we've picked for this one is the well validated and characterized, which was at an air temperature of 394 Kelvin. At this temperature, we expect that the vaporization process is pretty quick. So a lot of the governing behavioral changes would probably be dominated more on the chemistry side than on the spray side. So with these small changes in droplet sizes, we don't see a significant difference in the global characteristics. However, we still did want to understand a little bit more of the localized behavior and the localized changes, because a lot of these localized changes can then subsequently impact what kind of durability we might be looking at. If the flame shape is changing significantly, if there's a lot of impingement on the walls, how the heat transfer behavior might be changing, all of that has subsequently long-term consequences, even if the global characteristics don't show changes. So in order to understand some of that behavior, we looked at defining different regions within the flow. So this is just again, you see a center plane slice of the referee rig with the velocity magnitude with the critical flow features of the central recirculation zone. You have the swirling flow shear layers, and then you have the corner recirculation zones. So we basically divide up this into region A, which just comprises the central recirculation zone, and region B, which are comprising of the corner recirculation and the swirling flow shear layers. And we wanted to look at an analysis of what happens in region A versus what happens in region B, as all of these regions are close to the nozzle exit. So what you see here is for just region A, the baseline probability distribution for the droplets. If I overlay that with the -5%, we don't significantly see any shifts. We do see a higher probability for smaller droplets, which I think is expected since this is reducing the droplet sizes, the mean of the droplet sizes. For the +5%, we see this shift towards a slightly higher numbers. Again, it's not completely unexpected because we are increasing the size of the droplets. If we similarly look at the ±10%, the -10% looks similar to the -5, wherein again, the location of the peak doesn't change. And for the +10%, the location of the peak is changing. So basically, we do see that an increase in the droplet sizes leads to shifts in some of these distribution towards larger droplets in that region A, whereas the smaller droplets don't seem to be, the distribution doesn't seem to be changing significantly. Now, if you focus on region B, which was outside of that central recirculation zone, again, looking at the baseline, we see that now in this case, the -5% shows a very slight shift towards the left, and the +5% doesn't show significant shift. You can see it's almost overlaid with the baseline case. And similarly, for the ±10%, we see that in the reduction side, we do see a shift towards smaller sizes. And when we increase it, we don't see a significant shift in these sizes. So overall, when we are reducing the sizes, we are seeing that the distribution shift shows smaller droplets. So we do see a different variability or the sensitivity of the droplet sizes in these different regions within very close to the nozzle exit, and how they're responding to smaller and larger droplet sizes. And the consequence of that is really looking at, again, a flame behavior and flame dynamics. The next thing we looked at was looking at temperature and flame anchoring. So we defined this using the 1200 Kelvin isocontour, flame anchoring location defined as the closest to the nozzle location, and then a spread, which was defined by the maximum distance in the radial direction. And we notice with the baseline sitting at the center, we see that there is some shifts in the flame behavior as well for these different cases, with the flame anchoring distance on the left and then the flame width on the right-hand side, again suggesting some localized behavioral changes as we are looking at changes in droplet sizes. The next one that I want to cover is looking at microgas turbines with applications for power generation, and we use blends of hydrogen and natural gas here. So what you see here is a slice of this combustor with 100% natural gas on the left, and then varying percentages of natural gas, and whatever is not natural gas is hydrogen. You can clearly see that there's change in how the flame anchoring is going, particularly when it's stabilized versus when there is flashback that's occurring, and the flame and the higher temperature, which is defining the flame, is moving more and more inwards towards the injectors. So we wanted to understand some of these behaviors and characterize the emissions characteristics as we went through a whole range of operating conditions. So this table here summarizes the model. So we are using grants for this one. We did use a combination of, looked at both just the transient simulations and the steady state simulations for this case over a range of operating conditions. So as the power load is changing, you can see that the air flow rate and the fuel flow rate are also changing. So are the outlet pressure for this specific microturbine combustor. So the video on the left shows a summary of the mesh. So again, we've used adaptive mesh refinement for velocity and temperature, and specific regions within the injector are embedded, which have many small pathways. So we just wanted to ensure that the flow coming in through is properly and correctly resolved. So as we looked at steady state and transient simulations, so what you see is the transient on the left top and the steady on the bottom right. There are some variabilities. Again, the global characteristic behavior, which, for example, the maximum temperature, the mean temperature in the combustor region, and the ppm of carbon dioxide don't show significant changes. But we do see note differences quite a bit between the transient and the steady cases for NOx predictions in this case. And part of that can be alluded to the transient behavior that you see on the top, wherein it does stabilize, but but the flame does tend to move a little bit inward and then come back outward and restabilize again, which is leading to incomplete combustion and hot spots within the combustor, which is where some of the NOx is actually showing these differences. Whereas the steady one does, for the most part, show a stabilized flame, which is not necessarily representative of this specific realistic condition of kilowatts. So we did, as a part of this, understand where steady state could help us out and where we had to be using transient simulations. And some of that was also shown through the results that we had from the emissions. So we had experimental data, which is shown by dots in here, the steady simulations with the square, and the transient with the triangles. And you see CO2, CO, NOx, and the unburned hydrocarbon, the total hydrocarbon that's at the exit of the combustor. For different loads, so the green dots here are the 30 kilowatt. For the most part, you'll note that the squares and the triangles from the simulations of steady and transient are very close to one another, except for when we were looking at NOx, which was what I presented on the previous slide as well. But as we go towards higher power, which is the 50 kilowatt, those deviations also start going away. So as we get towards stable conditions where there is no flashback, the steady state simulations can do a pretty good job in predicting the emissions. Whereas where there is a lot of transients, it is understandable that the transient simulations is doing slightly better, or gives us a little better idea of the dynamics compared to the steady state simulations. And similarly, we did this for the 65 kilowatt as well, just looking at how these emissions are changing. With that, I hope I've given you a little bit of a preview into some of the work that we've done here at Argonne, looking at aviation gas turbines and hydrogen gas turbines and micro turbines in this specific case, using Converge. And we've applied it to a bunch of other applications as well, into large scale hydrogen gas turbines, into different sizes of aviation gas turbines, like a mid-size RQL combustor and a small size combustor, which is based on the trap vortex combustor concept. With that, I thank you all for your time, and I'll be happy to answer any questions.